All right, hey, how's everyone doing? I wanted to go over what I thought was a really good question on the ACES worksheet that involved energy, light, and Avogadro's numbers as it pertains to moles of photons. So reading this question, we see that a nitrogen gas laser pulse with a wavelength of 337 times 10 to the negative 9 meters contains 3.83 millijoules of energy. How many moles of photons does the laser pulse contain? The majority of students see this question and get a little confused at how to approach this question because they are concerned with where do these values fit in to a equation. And so what I wanted to do was approach this problem and hopefully get some conceptual understanding across about why this problem needs to be approached the way it does. So one of the major components of what I see students making a mistake is they are not necessarily familiar with the concept that a laser pulse is effectively a package of laser energy. That means that a pulse of a laser is a amount, right? It is set. That pulse shoots at one particular amount. And we have a value on how much energy that pulse contains. However, as we learned from equations such as E equals h nu and E equals hc over lambda, that a photon has the same wavelength of any light, right? Because light has wave-particle duality. So the wavelength of any light is the wavelength of an individual photon. That is the differentiation that you must make, I think, to be able to approach this question more appropriately. Therefore, if we know the wavelength, we can calculate the frequency. And if we know the frequency, we can calculate the energy of a single photon. And once we understand that a single photon has an energy that is different from this energy here, this is not the same as the energy of one. This is the energy of the package. Similarly, you could say that we know that there are eggs in a carton of eggs, but how many eggs are in that carton, we would have to count or know that it is 12. So approaching this problem, knowing that the pulse contains 3.83 millijoules, and this will help us determine the number of photons in the pulse, the first step is to find the energy associated with just one photon of that wavelength. So the energy of the photon in this case would be equal to hc over lambda, where h is Planck's constant, 6.63 times 10 to the negative 34 joule seconds, and c, 2.99. You may see this written as 3, that's okay, meters per second to the negative 1. And this will be all over the value that we have, 337 times 10 to the negative 9 meters. Now, once we plug this in the calculator, we have a energy. And I will quickly compute this. 34 times 3.99 e to the 8 divided by 337 e to the 9. And it looks like 5.88 and I'm sticking with the significant figures here, times 10 to the negative 19 joules. Notice that this value is not the value here, okay? And the reason for that is because this is the energy of an individual photon, not the pulse. Remember, the pulse is a package. So what we must do from there is take that value along with the number of millijoules and find out what that is. So what we would do is we would take that value of 3.83 millijoules, and we would convert that to joules. And that is done like so. Now we would utilize our energy here, but recognizing that if this is the energy of an individual photon, we can place this in our dimensional analysis using just that. .88 times 10 to the negative 19 joules per one photon. This dimensional analysis, in my opinion, is likely where the majority of students may be confused, because a photon is not a unit of measurement. It is a entity that we are counting. Okay, it's an entity we are counting. And if we recognize that, then we recognize that the question is asking us about a mole of whatever it is that we're interested in, which in this case is photons, and therefore we need to use Avogadro's number. So now we have effectively a two-step problem, conversion from millijoules to joules. We can see, or we should be clear, that we have converted our units. Joules have now turned to number of photons, and then number of photons, which is what Avogadro's number tells us, the amount, and per 1 mole. So once we do this computation, we will have number of moles of photons. And that would be 1.08 times 10 to the negative 8 moles of photons. Okay? Or 10.8 nanomoles, depending on how you want to report that. So again, really quickly, the pulse contains a amount of energy that is directly proportional to the number of photons. How we can determine the number of photons, we utilize this very first calculation to determine the energy of the photon, and then we utilize a method using dimensional analysis to convert the energy of the pulse to the full energy of the number of moles of photons. All right. Again, if you have any more questions, feel free to send me an email.